So welcome to another edition of Papers We Love Too in San Francisco. I'm Elaine Greenberg. I work for Fastly, and
I'm Inés Sombra. Yes.
Inés is also here. So welcome to Fastly. This is the first time we're doing Papers We Love in a different space since we've started in San Francisco. All right, Fastly is a content delivery platform, network, whatever you want to call it. We're really flexible and transparent. We have a great API, a great dashboard. We're also hiring, which if you want to help make the web faster and work with really awesome people, come chat with me or any of the other Fastly people here. Also, if you are a part of another meetup or community project in San Francisco or beyond, please let me know how Fastly can help. We love helping meetups and the community in general, and we're always looking to help out more. So just come find me and we can chat.
Yes. Yeah. All right. It's my turn. Yeah. All right. So we have a lot of things to discuss before we start. Just kidding. It's not a lot of things. So this is Papers We Love. I see a lot of new faces. I see significant number of faces that I haven't seen before. So this month, I guess I should answer like what we're about, because I got asked this question a fair bit, and I don't really necessarily think that the group knows yet. We've been meeting since February, so the idea is to get to make academic research more accessible to people that may not necessarily be academics, and it's really nice that we get friends and help from academics like Peter this month. So my particular take is like if you are out of grad school or if you really enjoy your undergrad and then you want to get back into the habit of reading and parsing and getting exposed to this type of ideas, then hopefully you will continue to return. Also, if you have a paper that you really love or something that made a mark on your career as an engineer or a practitioner or however, or like scientist or whatever it is, a ninja, rockstar, coder, and you really want to share it with a group, just reach me, tell me, and then I am collecting or I'm assembling the 2015 lineup. 2014 is already booked, so I'm going to let you know who we have. So in September, we're going to have Armin from HashiCorp talking about Zwim. In October, Carl Kingsbury comes to talk about a paper that I don't yet know, but I'm sure it's going to be either hilarious, difficult, or whatever it is that Carl decides to do. In November, we have Leif Walsh from the New York City chapter, and he's going to talk about like data structures and specifically level ancestor simplified, so that should be pretty nice as well. And in December, we have Peter Baelish closing the group, so I think it's pretty strong till the end of the year. Come back, let me know if there's anything that we could do to make this more accessible or friendlier to you. And the bathrooms, this is a new venue. If you need them, are like around just as if you...
Out of the office and to the left. Yes. Out of the office, so just through there, and then to the left, you'll see signs for the bathroom.
Yes. And the format today is going to be slightly more structured, as in we have designated a bar, so we can continue to drink after today. Yeah, so we're going to Mars Bar in the corner of 7th and Brand. Yeah, we'll go as a group, so just follow everybody. So without further ado, let's give it to Peter, our speaker today, Peter Alvaro.
Hi, everyone. Thanks for coming. Thanks for coming to SOMA to talk about epistemic modal logic with me when you could be driving to the playa, to drink frozen margaritas in a chilled tent with Mark Zuckerberg or whatever it is that you do out there. So thanks for sharing this time with me. And a special thanks to the organizers for inviting me to be part of this community. I love reading papers and I love talking about them. And it's really been a long time since I've talked about something besides my own research, which gets kind of boring. So it's fun to talk about somebody else's research. The pressure's like a little bit off, maybe. So today I'm going to be talking about Joe Halpern and his collaborators' work on using knowledge and knowledge theory to reason about distributed systems. I'm going to be sort of celebrating Joe's work, and time permitting and audience permitting, I might be sort of incanting some of his work in the form of going through a really detailed proof. That's going to be up to you guys, because this is going to be a choose-your-own-adventure talk. I don't know too much about this community, and I guess Inés was indicating that maybe nobody knows, but I get the kind of sense that this community really likes, almost to the point of fetishizing, complexity and details. So I have prepared a very quite detailed proof of the fundamental result of this work, the proof that common knowledge is not attainable in a system in which communication is not guaranteed by any protocol. And we can go through and like do that proof. But I'm going to give you a chance about 2/3 of the way through the talk to take a vote and decide, no, let's gloss that so that we can start drinking earlier. I guarantee if we do that, the talk will go over an hour. If we gloss, it'll probably be a little under an hour, and I'll leave it up to you. Okay, so for those of you, and I don't see too many of you, but for those of you who were here last time at Papers We Love, Henry Robinson from Cloudera gave this really inspired talk about the famous FLP, Fisher, Lynch, and Patterson impossibility result. And that result sort of, the shorthand for that result that many people are aware of and get confused by as consensus is impossible. Obviously, consensus isn't impossible. The sort of longer hand of that is, in an asynchronous distributed network, any deterministic algorithm, and given an asynchronous distributed system and a deterministic protocol that solves consensus, there exist executions in which it doesn't terminate. That's sort of the precise statement of it. So along the way to proving this rigorously for us, Henry introduced this very interesting problem of distributed agreement, which is, arguably, but I would argue it, the single most difficult problem in distributed systems. How do we come up with algorithms that allow a collection of computers in a fault-tolerant way to act as one, right? But I would argue it's not a problem. It's a huge hierarchy of problems, and knowledge is going to help us understand the places in the hierarchy. Yes? Closer. Okay, that's not too loud? Okay. Okay. He also, along the way, introduced us to this idea of impossibility results, and in a sort of frustrating way, right? Because you're told there's this thing that you think you need to do, and indeed, you do it every day, right? Achieve consensus via protocol. That thing that you do every day, it's not possible. So how do you internalize that? How do you interpret it? How do you work around it? And then along the way, not so much in the talk, but at the end of the talk, he brought up this really, really tantalizing concept of weakest failure detectors. Like once you've accepted that you can't achieve consensus in a truly asynchronous network due to the difficulty of distinguishing slow nodes from dead nodes, well, what's the smallest set of simplifying assumptions you have to make to circumvent that impossibility result? Can we posit the existence of an oracle that breaks the rules? And then we can ask questions like, well, what's the simplest version of that oracle? So I'm going to address all these concerns today and more through a different lens, through the lens of like, let's talk explicitly about states and the growth in states of shared knowledge in a group. And in fact, let's invent a formal language that allows us to talk about that precisely, give it precise semantics, and use it to study algorithms. Okay? Now, in the sort of Byzantine fault-tolerant adversarial analysis and game theory communities, I think reasoning about knowledge is a very easy sell, right? If I want to make my right move in an adversarial game, it directly involves reasoning about what you know, that I know, that you know, that I know, right? So rich, nested knowledge is an easy sell in the Byzantine community. So if you're engaged in a battle of wits with a Sicilian and death is on the line, you certainly need to think about epistemic logic. But I'm going to argue today that even if we don't make those assumptions, we assume that, well, systems do fail, and if they can fail, if there's some way they can fail, they eventually will. But they don't fail in diabolical ways, right? They fail in failure ways. So, computers crash, maybe they come back, maybe they don't. Messages get dropped, messages get reordered. But there aren't actually demons trying to destroy us. Knowledge-based analysis is just as interesting in that weaker model, okay? So why do you care? Why do I care about this sort of stuff? Well, we're all distributed programmers because we write programs that have to run on lots of computers, right? And we do that. We decide to write a distributed program not just because we're masochists, but because we decided that the problem requires the cooperation of multiple computers. Maybe that's because we want to mask failures. Or maybe that's because our data size is so large that we can't process it all on one computer. We have to partition it. More than likely, it's both, right? We have to partition data and we have to mask failures. So we have to write some sort of non-trivial distributed program. The computers can't just sit there and do their own thing. They have to communicate and collaborate and things like that, right? But before we write the program, we should ask ourselves, well, how do we know if we succeeded in writing the program? What does it mean for a program to be correct? We should choose a language. Maybe it's English. Maybe it's some kind of logic language. And write down the properties that we want our program to achieve. An example of a property that you might want a program to achieve, let's say I'm writing a commit protocol. A property that I would want to maintain is, if one agent decides to commit a transaction, all the other agents better damn well decide to commit it too, right? So that might be my property X. So the questions we have to ask, well, the first question we should ask before we start hacking, right, is like, can you even get that? Can you do that? Is there like a protocol for that, or can you invent one, or is it just impossible? That's a possibility question. Knowledge is going to give us a unique lens for answering possibility questions, and also for sort of uniting a lot of seemingly disparate impossibility results from the history of distributed computing. In fact, I have it on hearsay that Yoram Moses, Joe Halpern's collaborator, said that he believes that all distributed computing impossibility results, including FLP, can be reduced to this much more fundamental problem of common knowledge being unattainable via protocol. Now, is that true? I literally have no idea, but he believes it. Let's say that we answer that first question in the affirmative. Yes, it's possible. Well, the next obvious and much more complicated question, I think, is, well, which protocol should I use, or do I have to invent a new one? And obviously, protocols have different costs and different models, and so there's this sort of stable marriage problem between a property that's written in some language, maybe just English, and a protocol that's written in some sort of low-level language, and the appropriate fit. If you choose too strong a protocol, it'll probably get you what you want, but you might pay too much for it, right? The messages might be too complex, the latency and throughput penalties might be too high. So you want to find the least expensive, according to some cost measure, protocol that achieves a particular property. Or maybe you're doing this Peter Baelish stuff, right? You're interested in available protocols. So there's a whole bunch of different protocols, and there's a subset of those protocols that have the property that they're available, that you can get a useful response from any node. They don't need to talk to a majority or something like that. So there's this really important fit question that we can also get a unique angle on by reasoning about knowledge. And then the last question is really just a language verification synthesis question that, like, how do I implement that protocol? How do I know if I got it right? Can you just implement it? Can you just synthesize it for me? There's three separate questions, three separate areas that knowledge gives us a unique way of looking at. So what do I keep saying knowledge. What does that even mean? So here are some strong claims. Feel free to disagree with me. What is hard? Distributed systems are hard, right? Does anybody disagree? Anybody think they're easy? So distributed systems are hard, and they're hard just because of uncertainty. And what do I mean by uncertainty? Well, there's the three big ones, right? The three big bugbears of distributed computing. Asynchrony. There's uncertainty about the ordering and timing of messages to be received. Partial failure. Along the way, some of the computers are going to probably crash. The more computers I use, the more likely some of them are going to crash. Do I still get a good result or not? And concurrency. Messages are racing. Who's going to win? Do I care who wins? So those are all different flavors of not being certain. But, like, what is uncertainty, really, to a philosopher? Well, uncertainty is just the great abundance of possibilities, right? I don't know something for sure if I can imagine two different states of affairs or more, and in one of them the thing is true, and in the other thing the thing is not true. I'll say something even stronger than that. Knowledge happens exactly at the point when I've accreted enough knowledge to have ruled out the last other possible world where something might not have been true. And for humans, like computers, knowledge, local knowledge, is the only possible basis for action. You base your actions on your local history. So knowledge is a great way to try to crack this nut of uncertainty in distributed systems because it's exactly the dual of uncertainty. Okay, here's another argument for why knowledge is a good way to think about protocols. Because knowledge has many surfaces, I can imagine drawing knowledge, like a triangle with a big K in the middle. Right? This is knowledge. Maybe it's a language. We're going to see how it could be a language in a minute. And so on one side of this is like protocols. Well, if we turn the lens on the protocols, all protocols are things that take actions based on their knowledge. Or, that's true of any protocol, even protocols that people use in politics. But a computer protocol, more specifically, sends messages based on the messages that it has received. So we can express protocols in terms of what you do when you reach a particular level or state of knowledge. So we can analyze protocols through the lens. Now, on the other side, we can put properties over here. Well, we can use knowledge to analyze the properties, too. Because what are protocols for? Why do we create them? Why do we reach for them? Because they're just things that get a group of communicating entities to a particular level of shared knowledge. That is the raison d'etre of protocols. So we can analyze properties in terms of how much knowledge is required, how deep, how nested, how global the knowledge needs to be to achieve a particular property. And we can use knowledge to bridge the gap between protocols and properties, right? To make it easier, given a property that we want, to know what protocol gets us there and not any further. And then, of course, the other surface is a much flakier one, which is like people, You know, we internally, before we even start to write down the pseudocode of an algorithm, describe it in English. And when we describe an algorithm in English, we almost always fall back because, oh yeah, by the way, we almost always fall back on you're talking about who knows what, and I know that I can garbage collect this memory when I know that you know that I know that I'm not going to use it anymore, or something like this, right? So, and if you're interested in academic papers about bridging the gap between application-level correctness properties and sort of the low-level mechanisms that either maintain them throughout the execution or achieve them during the execution, there's a great paper in SOC 2013 about that. It's called Consistency Without Borders. I'm going to be plugging my own papers the whole time because I don't know how not to do that. And so this is just an example of what I was saying a moment ago, that when we talk about how to implement a commit protocol, we talk about knowing. And we talk about states of nested knowledge. I know that you know, or in distributed garbage collection similarly. And if you do a Google code search for knows, Scholar search, you find in the informal descriptions of algorithms that it's pretty ubiquitous. Okay. So for a warm-up, even though I'm already 10 minutes in, I'm going to do an exercise that I used to do when I co-taught this distributed systems class with Joe Halpern at Berkeley. We're going to try to implement a reliable delivery protocol for two endpoints communicating over an unreliable network, a network in which communication is not guaranteed, okay? So Alice wants to send a message to Bob. She wants to say hi. But the difficulty is it might or might not make it through the cloud, right? So what's the problem with this straw man program? The problem is uncertainty. Not just uncertainty in the execution, because the uncertainty in the execution in the network is sort of taken as given. The real issue is the fact that that uncertainty in the environment translates into uncertainty about the outcome. We want to know that the message gets delivered. How can we know that the message gets delivered? Well, the obvious straw man is a sort of infinite retry approach. And I would argue this isn't really knowledge theoretical. This is sort of a brute force approach. Alice makes an uses a buffer to store the message and uses that buffer to drive retransmission of the message infinitely. Infinite storage, infinite behavior. But we can convince ourselves, using a probabilistic argument, well, the probability of success is non-zero, and we make an infinite number of attempts, so obviously, with probability 1, the message is going to get delivered. Okay. That's not a very satisfying proof, but we can convince ourselves of it. So what's the problem with this protocol? Well, one problem is that it's completely bananas, right? It stores high forever, and it sends high forever. And then maybe more fundamentally than that, because I think we can fix that, is the problem that it doesn't deliver the message once or twice. It delivers it infinitely many times. And this may not be okay, because the downstream processing after Bob may not be idempotent. It may not produce the same effects if it sees the same inputs more than once. And we might have reason to be concerned about that. See, there it goes again. So in our attempt to patch it up, it's tempting to apply a little knowledge theory. Well, this is what you would do anyway, right? This is what any of you would do. But whether you knew it or not, you would be using knowledge theory. Because the question that Alice has to deal with is, I have this infinite state and this infinite behavior. When can I, in a principled way, know that I no longer need to store that high or transmit it anymore? Well, I know that I don't need to when I know that Bob knows it, right? Well, how do I know if Bob knows something? Maybe he could send me an acknowledgement, right? So we update our protocol. We have Bob, when he gets the hi message, he generates a hi yourself message, and he ships that across the network. Of course, we keep retrying, because that ACK might get lost, too. And when Alice gets the hi yourself message, the acknowledgement, she knows that Bob knows hi, nested knowledge, so she can clean up her state. That's pretty cool. But of course, we haven't addressed the fundamental issue of at least once delivery, when what we really want is at most once delivery, right? Can we do at most once delivery? That seems hard. Well, let's see. Oh, by the way, if you're interested in a principled approach to automatically having a programming language know when state can be garbage collected because it won't change future behavior, there's a great paper about that in VLDB 2012 called Edelweiss. Okay, and then at this point in the lesson, sometimes a smart student would point out, or I would sort of Socratically force a smart student to point out, that there's a duality at play here. We used a buffer on the sender side to generate redundant behaviors to overcome loss. Maybe we could use a buffer on the receiver side to suppress redundant behaviors, like a dual buffer. That sounds cool. So what do? Bob probes the buffer when he gets a message, and if the message is in the buffer, he doesn't deliver it. if the message is not in the buffer, he delivers it, and if it isn't, he suppresses it. So we've achieved exactly once delivery. That's awesome. I thought you couldn't do that. So, no, but we actually haven't, though, because we have this problem of infinite state at the receiver, right? Now, all of a sudden, we got rid of Alice's buffer, we know when we can clean it up. We've got a buffer at Bob that needs to remain forever. Wait, why does it need to remain forever? Well, because of uncertainty, right? What uncertainty? Bob's uncertain about whether Alice is going to send the message again. He doesn't want to deliver it redundantly. Well, let's keep turning the crank. So what would he need to do to clean up that buffer? Well, let's see. He would need to know that Alice knows that he knows the message. If he knew that Alice knew that he knew the message, he wouldn't need to keep that buffer around anymore because he knew she wouldn't send it. Oh, I know, so we can just like add another ACK, right? So we can have this ACK, and it goes like this. Like, that's cool, and then Alice cleans up her stuff, and then Bob cleans up his stuff, and that works, right? Actually, shit. That last ACK might get dropped, right? So we could put a buffer back over on Alice. You guys see where this is going, right? What we can do is we can infinitely extend this protocol with additional rounds. And as we do so, we're in a really real way increasing the state of knowledge of the two participants. But the two participants are going to play hot potato with this infinite buffer. They're never going to get rid of it. Because there's some state of knowledge that they need to completely clean up all their state. Some kind of common knowledge, right? About the delivery, that they're never going to get there this way. And in fact, this reminds me of another piece of folklore from distributed systems. Can I see a show of hands of who's familiar with the two generals problem? All right, few enough people I can say it. So there's these two generals, Zod and Lee. And they're camped on top of these two mountaintops on both sides of a valley. In the valley, their enemy is encamped, and their enemy outnumbers them. So if they both attack simultaneously, they'll certainly succeed. But if either of them attacks independently, they'll certainly fail. Now, they can communicate with each other by sending mounted messengers through the valley to the next mountaintop, but there is the hazard of the messenger being ambushed. So the question at hand is, can Zod and Lee devise a protocol that can allow them to simultaneously attack? And the answer is no. And there's a bunch of different ways of proving this or providing intuition for this. The way we usually provide intuition for something like this is we say, well, so Zod sends a messenger to Lee. Does he attack? No, he doesn't, right? Because he's uncertain. He can't tell the difference based on his local history between executions in which that messenger successfully got to Lee and executions in which he was ambushed. So he can't attack because he might get killed. So he tells his messenger to ask Lee to send back another messenger. Does Lee attack? No, he doesn't, because he can't tell the difference between his messenger getting to Zod and not. And this is just like what we just went through, right? We're never going to actually get there. When you try to prove this formally, on the other hand, it gets a little bit gnarly and system specific. Most of the proofs of the two generals use something that's like can I see a show of hands who knows proofs by induction? Who doesn't know proofs by induction? Okay, great. A backwards induction sort of reductio argument where you say like, well, let's say that you had a protocol that did it, and it does it in k messages. Well, consider the execution in which the kth message is dropped. And then you kind of have to backwardsly induct back to zero. It's a pretty awkward proof strategy, right? So one of the things that's cool about this knowledge stuff is that it's going to give us a more elegant, universal way to prove results of this type. Okay, warm-up's over. Logic time. As this talk progresses, the formalism and the notation is going to get more and more oppressive. So I'm going to try to ease you into it. Right, so you guys know logic, right? Propositional logic. So we have like a family of variables that are either true or false. Right now I'm looking at Q and P. P might mean something, some proposition of interest for a distributed system. I have an implication up top between Q and P that says if Q, then definitely P. And so this might say something like, hey, look, acknowledged rights have to be stable. It's like a correctness invariant, a durability invariant. Okay? And it changed my Greek. It's okay. It changed my Greek to uppercase Greek. We use phi to indicate a formula of any kind. So Q is an atomic formula, psi, but so also is Q implies P, a formula. So we use psi as sort of a variable for formulas, and we connect formulas together with these connectives, like and, interpreted in the usual way. It's true if both of its operands are true. And not, it's true if its operand is false. And one of the nice things about symbolic logic is that we get these, oh no, what's happening? we get these nice dualities where we can define a really minimal core of connectives and define the other connectives as sort of syntactic sugar using duality, right? We don't need to define the semantics or meaning of or, because or is just not the thing and not the other thing, right? That's what or is. And implication, which you can't see, that's annoying, is, so if I say, phi implies psi, that is just to say it's not the case that phi holds and psi does not hold, right? That's the meaning of implication. And, dualities are really cool, so I'm going to dwell on them for a second. I think they're trippy. And I'm going to use this to introduce the idea of modal logics, which is what we're going to be talking about today. So you may have some familiarity with first-order logic. You probably know also in first-order logic that we have these so-called existential operators. There's some member of the domain for which a certain property holds, or maybe for all members of the domain a certain property holds. And in fact, we only need to define the semantics of one of these operators because it has a dual using negation. It is the case that there exists a member of the domain for which phi holds exactly when it's not the case that for all members of the domain phi doesn't hold. So we can use duality to define rich syntactic sugar over a minimal semantic core. Here's one that you probably don't have an intuition for, but these are the modal operators, diamond and box. What it means to say diamond phi is to say it's not box, not phi. And I introduced this in this way sort of backwards to emphasize the fact that logic is just meaningless symbols until we attribute a semantics to them, and it's the semantics that's important, not the intuition that we carry into the reading of the symbols. What's amazing about the family of modal logics is that they're able to capture, not just when a proposition is true or false, but when a proposition is true or false given a particular contingency, in a particular modality. And regardless of the vastly different interpretations that we can give to modalities, they have an almost identical semantics. Temporal logic, under the covers, is basically the same thing as deontic logic, is basically the same thing as epistemic logic. It's just our interpretation of the symbols are different, and we tweak the semantics a little bit in the way that I'll explain. So something is sometimes true, following the duality, if it's not always not true. Something's permitted if it's not obligatory that you don't do it. And something's possible if it's not known that it's not. Knowledge is a dual possibility. Okay, so let's get a taste of the language and see why it might be interesting to say things, to make these modal utterances about knowledge. So it's one thing for a right to be stable. We're going to take the box operator and give it a more intuitive name, K, for knows. And in order to be able to talk about the knowledge of individual agents and groups of agents, we need to subscript our operator by who's doing the knowing. So we might have an operator who says, it's one thing for psi to be true, so nobody might know it though, phi rather, but Alice knows phi is a completely other matter. And Alice knowing that Bob knows phi is different than that, and Bob knowing that Alice knows phi is different from that, and we can just keep going on like this. And we can say some pretty interesting things. Since we're interested in distributed systems and the knowledge of members of a particular group, we're also going to talk about group sugar for these modal operators. You kind of have to imagine that for all these E and C and G, that they're implicitly subscripted by the members of the group, whether that's like a list of names or some level of indirection where it's the name of the group that you can go look up somewhere else. But when the meaning is clear, when the context is clear, we'll just leave off that subscript. So it's one thing for phi to be true. It's another thing for everyone to know phi. It's actually a completely other thing for everyone to know that everybody knows phi. It might be tempting to say, well, maybe we can collapse these things. But we really can't. They mean completely different things, right? And one of the examples that Halpern gives is the rules that we apply when we drive a car, right? So I'm at a stoplight and it's green. Do I go? It's not enough for me to know that green means go and red means stop. I need to know that everybody else knows that green means go and red means stop, because otherwise they might go on the red light. And that's not even enough, 2 levels, right? Because I need to know that they know that I know, because otherwise they might drive in a skittish way or something like this. And the more you think about it, it's really hard to see where this terminates. Like, we sort of need a common, infinitely deep knowledge of the rules of the road to enter into the social contract of driving. That's weird. How do we characterize that? I've been using this phrase common knowledge sort of loosely. Let's define it more formally. And later we'll define it even more formally. So we could talk about a superscript E, which is like how many E's come before the formula. So E to the 100, there's 100 E's, it's 100 deep. And common knowledge is going to be the limit of that, right? As E's superscript approaches infinity. You should be beginning to get an intuition that it's probably hard to invent a protocol that gets you there, right? Oh, but before we get to the knowledge hierarchy, there's a couple of states of much weaker knowledge that protocol writers are going to be interested in. It's one thing for a write to be stable. Nobody might know it. And it might be the case that nobody knows it, but if you are somehow able to combine the knowledge of everyone in the group in a consistent way, then you can make somebody know it. You could centralize this distributed knowledge. That's cool. And if you did that, then you would get to this other weak, but strictly stronger level of knowledge. Somebody knows it. What can we do with this? Well, it turns out that these levels of knowledge arrange themselves into this really cool hierarchy. And the hierarchy is strict. Well, I shouldn't say the hierarchy is strict. The strictness of the hierarchy is going to depend on our distributed system model. If we're in a shared memory system, where everybody can just look up whether something's true, this whole hierarchy collapses down to nothing. But if we're in the standard model of distributed systems in which processors have local state, communicate via messages, it's a strict hierarchy. And to get from one level to the next, you need to send another message, at least another message. Now let me illustrate that for a second. Deadlock detection is a thing that you have to do in databases, and it's a hard thing if the database is distributed, because you have different partitions of the database. They each have their own lock manager that has a purview of what's going on in that particular partition. And you might have a deadlock, a cycle of transactions that are all waiting for each other, so they're stuck and can't do anything. You need somebody to go kill one of those transactions, abort it, undo the deadlock. The problem is that none of the local transaction coordinators know about the deadlock necessarily, because it might span multiple ones. So a typical centralized algorithm for solving the problem is all the agents forward their view of this graph to a central coordinator. And the central coordinator assembles the graph and does a cycle detection problem in it, and then takes the appropriate action, shoots a transaction. So you see what the communication pattern looks like, pretty darn simple. Well, that's not surprising, because what deadlock detection does fundamentally is achieve S of there is a deadlock, where phi is interpreted as there is a deadlock, and it is this. We start from distributed knowledge, and we combine that knowledge to get centralized knowledge, and that cost us messages. Let's look at another distributed algorithm, reliable broadcast. Now we have an agent who wants to get a message to a bunch of other agents and wants to make sure that it gets to them even if there are failures. And so in a failure-free execution, we see a communication pattern like what we saw in our toy example, where everybody acts, round-trip messaging. And that's actually not surprising, because reliable broadcast, all it really does is take something that someone knows, that message, and turn it into something that everyone knows. Right? And that cost us more messages than the other, more complexity than the other step. Is anybody familiar with uniform reliable broadcast? It's a bit of an academic thing. So almost any textbook protocol that you could think of, there's a standard version and a uniform version. The uniform version is harder because it dictates what correct processes have to do in the face of failed processes. So for reliable delivery, for example, the invariant, the correctness invariant, was something along the lines of, if a correct process delivers a message, then all correct processes must deliver that message. And the invariant for uniform is weaker. It says, if any process delivers a message, then all processes must deliver it. So you have to maybe change your... You can't dictate what failed processes do, because they might be crashed. But you can dictate what correct processes do based on what failed processes do. And the standard textbook solution to this problem is called the all-ACK algorithm. You don't deliver a message when you receive it. When you receive the message, you tell everyone else that you have it and are ready to deliver it. And when you've received that ACK from everyone else who's carrying out the same symmetric protocol, you know that you can deliver it. Well, what's happening here? Oh, I see what's happening, right? We're going from someone knows something, and we're jumping over everyone knows something, and going to everyone knows something. We're climbing the hierarchy with protocols. And part of doing that could be, right now we're looking at protocols and looking at what they do, but you could have inverted this and said, we're going to decide where we need to be in this hierarchy based on our correctness property. And we're going to go try to find the appropriate fit for a protocol. And you can imagine doing this for a long time. So, this might be your favorite, James Mickens' favorite, crazy BFT protocol. It's completely insane. It takes you up to some K that's absurdly high. But the point to take away is it's going to be some K. It's not going to take you to C, right? Because C is infinitely far away. We're never going to devise a protocol that gets us there. And yet, it seems like common knowledge is sometimes necessary to take action. So what the hell is going on? Okay, so for most of the rest of the talk, I'm going to address question 1, which is about impossibility, and show a methodology for proving fundamental impossibility results. And time permitting, I'll get through the other things. And I think we're at the choose your own adventure. Okay, so yeah, the big proof is, in a system in which communication is not guaranteed, in a system with that cloud, like the one I described, or with the assumptions of the two generals problem, with the ambushing armies and so forth, common knowledge of something that you didn't already know before you did any protocol, because then obviously you don't need a protocol for it, common knowledge is not attainable in any run. And we're going to show that the two generals, and Moses would say, all your other favorite impossibility proofs too, are just corollaries of this fundamental result about what you know and how that tells you about how systems work. Whew, okay, but it's a long walk. How are we doing for time? Yeah, so it's a long walk. So here's the choose your own adventure. Oh, so this is what the structure of the proof is going to look like. I'm going to talk to you about semantics. I'm going to do that anyway. Let's talk about the semantics of modal logic, because that's fun. Then I'm going to present a reasonable model of distributed systems. Then I'm going to try to focus on the neat trick that Halpern and co. did, which is to observe that model has this beautiful, rich, deep correspondence with the mathematical semantics of the logic. We can use the machinery of logic to reason about the real systems. We need to get some lemmas out of the way. There's the proof of the big theorem. And then once we prove the theorem that common knowledge isn't attainable, there's still one last step, right? We have to prove that the generals needed common knowledge to attack. And when we have both of those things, we can snap them together and get the proof of two generals being unsolvable. Let's do semantics, and I'll give you the chance to vote. So what the heck is semantics? For a computer scientist, semantics mean all sorts of different things. But to logicians, they mean something really, really simple and precise. You know, as I sort of indicated and showed you with these boxes and diamonds, syntax of logic need not have any intuitive meaning, and certainly doesn't have any real meaning. Semantics is what gives meaning. So most utterances that we're going to see in a logic are going to involve some formula. That's the Greek symbol phi. They're going to involve this so-called turnstile operator, which is actually a pipe and a minus, because I couldn't find the turnstile operator in LaTeX, in PowerPoint. And the way to interpret the turnstile operator is makes true, or entails. And then the thing on the left side of the turnstile operator is some sort of abstract mathematical structure that represents a world or a state of affairs. Because a formula isn't just something that's universally true, a valid formula is, but most formulas aren't something that's universally true. There's something that's true in a particular state of affairs, but not true in some other state of affairs. And so semantics is two things. Defining the structure that's appropriate to a particular logic language, and giving a set of rules that tell you how to hold the formula up to the world in a rigorous mathematical way and say, is this formula true or false in this world? So that's what semantics are. So I'm going to take us up through the logics and give you a little bit of intuition for how this stuff works. What the heck is that? Okay. Ignore the thing that looks like a colon for a second. So if we have a propositional formula like the one I introduced to you before, P and Q, and we want to hold it up to a structure and ask, is it true in some structure S? Let's first answer the question, what is the shape of S? Like, what is this structure? Or some people call it a model. Structure model, pretty much interchangeable. And what is this thing? Well, for propositional logic, the answer is it's actually really simple, right? All we need is a mapping from the names of the variables to whether they're true or false. There's one state of affairs where they're both true. There's one state of affairs where neither is true. You see where this is going. There's one state of affairs where one or the other is true. So we basically just need like a hash map whose keys are names of variables and whose values are Booleans. And then in addition to that, we need a set of rules, one for each logical connective, that tells us how to take a formula and hold it up to the structure and see if it's true. So for example, we might see a rule for and that says something somewhat tautological but necessary, right? We can say that phi holds in the model S exactly, phi and psi, rather, hold in the model S exactly when phi holds in S and also psi holds in S. Right? So that's our semantics, two things. Describe the structure, describe the rules that you use to hold a formula up to the structure. You probably have seen first-order logic, which allows us to express much richer things than propositional logic, because we're not just connecting propositions that are true or false. We're making statements about members of a domain and their relations among each other, right? So we can say these cool things like, look, all dogs are big and they all like me. This is obviously something that's not going to be true in all structures, but is going to be true in some structures. So the question we want to ask, as we did on the previous slide, is what does that structure look like and what do the rules look like? Right? To be able to say, for some structure S, is this true or false? Well, it's not enough to just assign variables to true or false. Now we need to think about members of a domain and what sets they're members of and what relations they have to other members of the domain. So essentially, the easiest way to think about it is we need a structure that puts records of arity that matches the predicates into relations. We need a database. The structure for first-order logic is just a database. And that's why first-order logic is such a great way to write queries on databases. And from an appropriate level of abstraction, if you think everything is a database, as I do, then everything can be sort of written in first-order logic with the appropriate extensions, right? And then you're going to also need some rules to, you sort of can reuse those rules about what and means from propositional, but you need to define like quantification, right? So you'd have a rule that says, S makes for all x phi true exactly when, if you take every member of the domain S and you create a new structure that's just like S except it assigns D to X, if that makes phi true for every possible thing. That's what all means, right? If you take everything in the world and you substitute that in. And so, a structure, as I just said, is a database. And it's awesome when we can take a rich expressive logic and look at its mathematical semantics and find this connection between that and like structures that exist in real life, things that we program, right? Behavior of distributed systems, the contents of memory. This is the stuff, right? And so, in this structure, that sentence is false, right? Because indeed, there exists a dog, Rover, who ain't big. And that's enough to disprove this statement, right? But in another structure, it might be true. If you're interested in the subject of using logic to program general-purpose distributed systems, a couple great papers about that. So Boom Analytics and Eurosys 11 or 10, my team implemented like a Hadoop HDFS stack in logic, and then I do declare Paxos in logic. But of course, today, we're supposed to be talking about modal logic. So let's jump to modal logic. So we'd see utterances like this, where we're not just interpreting what it means for P to be true or false and what that means for the overall formula. We need to interpret P being true or false in a particular modality with respect to a particular contingency. Maybe a temporal one about things happening before each other or after each other, or maybe in an epistemic one about who thinks what is possible, right? So we need a richer structure than we had for propositional logic, even when we're dealing with propositional variables. Intuitively, we need a structure that captures the idea that there are multiple possible worlds that are maybe connected with each other in some interesting way, right? So Kripke structures are the classic way to attribute a semantics to modal logic. And a Kripke structure is just a set of possible worlds, W, possible states of affairs. And in each state of affairs, certain propositions are true or false. But a proposition being true in one world doesn't mean it's true in another. So we have this function pi that essentially assigns a propositional semantic structure to every one of those possible worlds. You imagine a function that you parameterize it with, what world are we in? Okay, and what variable are we talking about? And now I can say true or false, right? Where the original propositional one, you just ask for the variable name, okay? So we got pi, and then we also have this R, which is a binary accessibility relation that says how worlds are connected to other worlds. And it's exactly in the interpretation of this accessibility relation that the distinction between our various modal logics, temporal, deontic, and epistemic is going to come out, right? So before I say any more, let's just imagine that this was a temporal logic utterance. Let's say that P means the system is deadlocked. Q means there was a request, and R means there was a response. So this would be a really great correctness property, combining a safety property. The system is deadlock free. It is always the case that not deadlock. And a liveness property. If there's a request, then there is eventually a response. So that conjunction of them would be like a good correctness property for a live system. A Kripke structure for temporal logic can be viewed as a directed graph, right? Where the circles, the nodes, are the worlds. They're labeled with the propositions that hold in them. And the edges represent reachability. Well, what kind of reachability? Well, in temporal logic, we mean reachability by making transitions in a state machine as we move forward in time. And this insight that I just sort of hinted at was the slam dunk that got Emerson and Clark their Turing Award for model checking, right? It was like, oh my gosh, like this mathematical structure looks just like a state machine. If we could programs are just state machines, if we could extract the underlying state machine of a program, we could just check formulas that say the program is correct on it automatically. We wouldn't need to do all this proof crap. We could just turn a crank, right? So that got him a Turing Award. Hey, this structure, that's just a state machine, sort of like that other structure was just a database, right? That's really cool. And so in this one, the first clause holds because it's never the case that P. But the second clause doesn't hold, right? Because there's a set of transitions I can make where I get to Q and Q is true, but never eventually R from there. So this correctness property was violated. We say, oh, it's a counterexample. Here's a counterexample. That's model checking. Now, in epistemic logic, we have a really similar structure, but the arrows are a little different because the arrows don't capture reachability in time. They capture possibility for a particular agent. So in this case, let's interpret R to mean it's sunny in San Francisco. There's two agents, I and J. I imagines two possible state of affairs. One of them, it's sunny in San Francisco, and the other, it's not. J imagines two possible state of affairs that are different, but with respect to that one proposition R, they're the same. So we can say something like, it's sunny in San Francisco, and I doesn't know it, because I can imagine a world in which it's not. And I knows that either J knows it or he doesn't, which that's kind of just law of the excluded middle stuff, right? And we can say, oh, J knows that it's sunny in San Francisco, but you know what? J doesn't know that I doesn't know, even though I doesn't know. J doesn't know that I doesn't know, right? Because in the two worlds that J considers possible, I guess the point to make is J doesn't consider S1 possible, right? Wow, that's cool. Okay, now it's time to stop with the semantics and connect them to a real structure in real life. And that's fairly easy to do. Here's a model of distributed systems, at least the left part of which I think you're familiar with. Processes communicate. They have their own timelines that they can perceive, but they can't necessarily perceive each other's timelines. But they can communicate by messages, which move through space and through time. This is a so-called Lamport diagram. P1 sending a message to P2, P3, and P4. In order to make the proofs go through, we're going to posit the existence of another line, a sort of God line, an idealized timeline. Well, that's not possible in distributed systems, but don't worry, no one can see it. We're just doing it so that we can establish cuts. So we talk about a cut, a point in a run of a distributed system, RT, is a cut on that line. So we might want to study a cut and study the properties of knowledge above the cut. In particular, we're going to be interested in the local history of individual processors, since as I argued, your history is the only basis for your knowledge, and your knowledge is the only basis for your action. So we're going to say H of P4 RT is just saying everything that P4 knows as of time T in run R. This is just one run, but it's going to be useful for us to talk about the whole set of runs generated by a protocol and an environment. We'll call that a big R, right? So R is like all the possibilities, all that uncertainty that makes all this so unbearable to reason about without the help of computers. Oh, H is the local history of a processor. So it's like what the sequence of messages and the initial state of P4 as of time T in run R. Okay, so as I said, the notation's going to get more and more tedious and cumbersome. Here we go. So a knowledge interpretation, we're going to define knowledge interpretation I as a structure, R, pi, and a set of V's. Check out the Kripke structure. It's the same damn thing, right? We can map this directly to a Kripke structure. In this case, we have a set of runs, okay? We have a function pi that has exactly the same meaning that it did. If you give me a run and a time, then I can tell you what propositions are true or false at that run and time. And then what we're going to do is we're going to partition out that accessibility relation, R. We don't just care about what's known. We care about who knows it. And since knowledge is a local phenomenon, we need a sort of copy of a reachability relation for every agent in the computation. So we're going to have a view relation for all the different agents, where like 1, 2, and so forth are the names or the addresses of the players in the game. Okay, and this is the worst slide as far as notation, but once we've done that, oh man, everything got pushed around, and once we've done that, we can establish a complete semantics for our epistemic modal logic that is rooted in a structure which works just like a Kripke structure for the point of view of checking, but which corresponds with actual behaviors of actual systems. And we just sort of do the obvious thing, like if something's a ground formula and pi says it's true, then it's true. And similarly, if it's not true. If we want to check if an and is true, we just check if both things are true in the structure. And then here's where it gets interesting. We can say that I knows some formula phi at a point RT in some run if all points in any run that processor can imagine also makes phi true. So if all points and all runs that are indistinguishable to a particular processor make something true, then that processor knows that that thing is true. That's what knowledge is, semantically, right? When I have the same view, I can't distinguish. And then everything else we can just define as sugar on top of that. Yes?
Can you say it again? Because I missed it. So can you say it again?
The knowledge part, or the, okay, so we have a formula that says, I know that the system is deadlocked.
Okay.
When can we know that, if that's really true that I know it, at a particular time in a particular run? Well, exactly when we can show from among the whole big set R of all possible runs that by looking at my own local history, I can't distinguish from this current run. Take the set of runs that look just like this one to me. If phi is true in all of those runs that I can't tell apart, then I know that phi is true, because knowledge is the dual of possibility. There's no possibility that I'm aware of in which it's not true. I'll also add for the philosophers out there, everything I've said about knowledge so far, you could just as easily say about belief. They have the same semantics. Usually what you do when you're trying to distinguish between knowledge and belief is you add an axiom that says, if someone knows phi, that implies that phi is true. That's the difference between belief and knowledge, right? Knowledge is belief in true things. So we just add the axiom. That's kind of philosophical Okay, so are we good? Okay, and then these other ones, I don't have time to get into, but they're defined just as syntactic sugar using dualities in the obvious way. Okay, this is the choose your own adventure part. I don't really like proofs. I don't like reading them. I'm the kind of guy who's usually like, man, you had me in at the intuition. This is so painful. But sometimes you need to go through it, right? Because the pain is the price that you pay to be absolutely certain about something. I also don't have a lot of experience doing proofs, because in academic talks, which I usually give, you don't do proofs. First of all, because they only give you like 15 minutes to talk nowadays, and wouldn't even be time to set it up, let alone knock it down. But also because nobody wants to hear the proof, right? They just want to hear the big picture, and if they think your stuff is interesting, then they'll decide if they think you're full of shit. If they think you're full of shit, then they'll go read the proof in the paper. But it's very rarely the case that you do the proof. Anyway, but I have a proof, because of that whole complexity worship thing I was talking about. So I'd like to see a show of hands. We could either wrap this up in about 10 or 15 minutes, or maybe a bunch more than that. Who wants to dive into the weeds and do the proof? Oh, that's not enough people. All right, so it looks like we're going to gloss the proof, and we can do it offline. It's actually like, really pretty painful. And I figured after showing you the semantics, you would be like, oh God, get me out of here. All right, cool. So I am going to walk through it, but I'm going to really gloss it, right? So one of the main points to make along communication's not guaranteed. Look at this stuff, man. Isn't that terrible? So it's possible that people stop receiving messages. It's possible that there's windows of silence, all this kind of stuff. We're going to need that for the proof. This is a really interesting lemma that gets used like 3 times in the proof. And I don't prove it here, but I think it's an interesting thing to discuss. So the idea is, if there are 2 different runs of a protocol, and there's just one agent, P, from the perspective of whose history the runs are indistinguishable, if there's just one agent who can't tell the difference, then it must be the case that if something was common knowledge in the first, then it's common knowledge in the second. Why is that? Well, because common knowledge requires that it is shared by everyone, right? And because my knowledge is just a function of my local history, in 2 runs in which I have the same history, I have exactly the same knowledge and exactly the same view of what's possible. Because my, meaning P's, participation in knowing if something is common knowledge is required for it to be common, if there's even one person who can't tell 2 runs apart, then it must be the case that if something that was common knowledge in one of them, then it's common knowledge in the other. And this is going to be the main hammer that we use to hit the nails in the proof, or that we would if we were doing the proof. It's a proof by induction, and it's gnarly. There's a base case where you say, well, if no messages are received, then obviously if something's common knowledge in one, it's common knowledge in the other. And if a message is received, I can construct another execution, it's starting to sound just like Henry's stuff, in which somebody received a necessary message, but in another run they didn't. And so I can prove by using my inductive hypothesis that if I assume that all smaller runs had this property, I've just shown that Any run that's one bigger than that has the property. Okay, that's the gloss of the proof, QED. And we have to prove another thing. Oh man, now we have to prove that the generals require common knowledge to attack. And this is a fun one that I'll do offline or at the bar if anybody's interested. This is a cool one that richly uses this knowledge theory. And then sort of the coup de grace, you say, well, okay, two generals. Obviously, the generals aren't going to attack if they don't exchange any messages, because by assumption, they're devising a protocol to attack, right? Otherwise, we wouldn't be having this conversation. So, now, I've proven, or I can prove if you want, that you can never achieve common knowledge via a protocol. I already provided the intuition, right, with the visual metaphor. We just needed to rigorously prove it. And then, because the generals require common knowledge, and you can't get common knowledge, and they didn't start with common knowledge, they're never going to attack, right? Okay. So where are we now? We're exactly where we ended Henry's talk. You need common knowledge to agree about certain types. Common knowledge is a thing, and sometimes you need it. But you can't get it with a protocol. So what the hell is an agreement protocol anyway? What is consensus? What are we supposed to do? Yeah, right? So Halpern himself says it's not just you, it's weird, right? I wouldn't agree with Halpern that it's paradoxical. I don't see anything like proving its own negation here, like logically. I just see something that can't be true because it doesn't jive with what I see in practice. So what the hell? How do we explain that? Well, the first one to make, and you can make this one about Henry's proof too, right, is that we've assumed that our protocols are deterministic. FLP assumed that protocols are deterministic too. It's nice to have deterministic protocols. They're a lot easier to reason about. The last thing you want to do is implement a non-deterministic protocol for something you could have implemented a deterministic one, because that increases the uncertainty. It makes it harder to reason about your system, right? So deterministic protocols are great, but we're not restricted to do them. And in fact, it's been shown, the Ben-Or consensus algorithm, that if you flip coins, you can achieve consensus and terminate with probability 1. So once you throw out the determinism assumption, a lot of these impossibility results go away. Another one is that we've been playing it loose and lazy with our language. Consensus, agreement, simultaneous agreement. There's millions of different flavors of agreement. And they require different concrete costs to achieve, and some are impossible to obtain. But most often, the ones that are impossible to obtain aren't the ones you want anyway, right? So what we need to do is study well the levels of knowledge that your properties need. Try to get the right protocol to fit the property, right? And obviously, this is one that we can shoot holes in. I mean, in real life, systems fail, and if something could go wrong, it probably will eventually. But it's not the case that there's like a demon in the network who chooses exactly the packets that you most needed to get through to drop, right? And so in real life, we see a lot of simplifying assumptions like, you know, the network partitions, but partitions heal eventually. And, you know, there's periods of connectivity that are like long enough to get enough rounds of protocol done that you can make progress or something like this. Alas, these sort of simplifying assumptions are pretty damn hard to encode into a formalism. So you just kind of hand wave and say, well, it's impossible, but it's not really impossible, because a network isn't really asynchronous. It's like partially synchronous or something. It's a little hard. Another approach to kind of achieving the same thing in a different way is to exploit something that came out of these proofs. Like, we didn't prove that you can't have common knowledge. We proved that if you have common knowledge, you started with it. You didn't obtain it via a protocol. And there's lots of interesting ways that we can exploit sort of bootstrapped assumptions about common knowledge, like the one about the rules of the road. Let's just look at a couple of them for a minute. Well, the weakest failure detector that Henry talked about, right? Like, the reason that works, so we can't solve consensus in an asynchronous network because it's impossible to tell delay from failure. But what if somebody could tell delay from failure? Can you use them? It's a way of sort of encapsulating and pushing into a corner an assumption that makes something possible so that you can study the rest of the system in a principled way. It would be much harder to try to change the execution model and achieve the same thing. We say, like, no, there's an oracle. It doesn't really do a failure detector, but it's good enough. What's the weakest properties we need from that to be able to get on with our lives? That's one approach. Another approach that I think is really compelling, feel free to disagree with me, is this TrueTime API and Spanner, right? Like, what's happening is everybody comes into being having a global clock that's accurate, but not just that, knowing that everybody else has a global clock that's accurate, knowing that they know, that I know, that you know, that they know, infinitely deep. Because we wouldn't be able to use this global clock to actually synchronize and order things unless we knew that it was common knowledge that we're born with. Now, maybe the global clock is a fiction. It's hidden down in funky hardware stuff that I don't understand. But let's just treat it as an oracle. We can treat it as bootstrap common knowledge and get on with our lives and simplify the protocols that we have to use to implement a globally distributed database. That's cool stuff. And then, of course, in that simple example, maybe some of you were thinking, hey, my state doesn't grow without bound. I'll like do some neat trick, to store my buffer. I'll just store the IDs, or I'll store sequence numbers, and I'll just store the high watermark of the sequence. And of course, those are cool. I'll just store a Bloom filter. I don't know. Those are cool engineering tricks, but they don't solve the fundamental problem because you're just taking something that grew linearly and turning it into something that grows logarithmically. But eventually, you're going to overflow your integers, right? But of course, in real life, the way you work around that in a protocol like TCP is you assume common knowledge about how many messages could there possibly be in a TCP session. Well, certainly not more messages than you can put into a 32-bit or 64-bit integer, whatever it is nowadays, right? So we assume that everybody knows that it's okay to wrap the sequence around and start at 0, because there's no TCP session that has jillions of messages in it, right? So assuming common knowledge is super common. We just need to kind of know how to point it out. Put a wrapper around, put a shell around it, kick it down into one corner of the system. Oh yeah, right, so what else can we do with knowledge besides all this impossibility crap? Some other things. Hazel-Ardakos, very, very recently after the publication of Halpern's work, did this amazing work with commit protocols, where he used knowledge theory to show, first of all, that all the variants of two-phase commit, with wildly different topologies, message complexities, et cetera, the thing that they all have in common with each other, besides their name, is the fact that they all achieve exactly the same level of knowledge in the hierarchy. And in fact, he went on to show that two-phase commit family of protocols achieve the minimum knowledge necessary to be able to safely commit. And further, he showed that the three-phase commit protocol achieved the minimum level of knowledge necessary to non-blockingly commit, according to a particular definition of non-blocking. And finally, he established a lower bound for how many messages you need to commit. And it turns out it's one of the more rare protocols, so-called linear 2PC, where people talk in a line rather than going out and back. So we got lower bounds for protocols. We got optimality of protocols. We got to explain existing protocols, why they're used, where they're used. It's awesome stuff. If you're interested in the subject of fitting coordination mechanisms, the cheapest available coordination mechanism to a particular problem, there's a great paper in ICDE 2014 about that, Blazes. Oh yeah, and then there's the whole language design, verification, synthesis surface of this. I forgot about that. So Halpern and Fagan early on did this really neat work of coming up with a couple of programming languages for protocols that explicitly use knowledge. And the flavor is like, it's a language of guarded commands and actions, right? Except the guards are about local knowledge. So you might say like, look, if you know a message and you know that everyone's acted, then deliver it. But if you know a message and you don't know that everyone's acted, then you relay it to everyone else again or something like that. So it's kind of cool, kind of old-fashioned looking, but cool. And much more recently, this guy Matteo Interlandi, I should have capitalized his last name, who's a postdoc at UCLA right now, took this language for distributed programming called Dedalus, really cool language, and extended it with epistemic operators so that you can like express two-phase commit, where you're like, okay, you log in a board at the next time if there's distributed knowledge that there's a no vote. And you go figure out what protocol you have to synthesize to consolidate that distributed knowledge. So essentially, he's made a truly declarative two-phase commit, where he just says, here's what you need to know to take actions. And you just go figure out how to make it so. Right? So that's super cool. And if you're interested in Dedalus, there's a great paper about Dedalus. It's called Dedalus. And just sort of to close up, because I'm almost at the end of the talk now, I'm interested in this subject, and when I was teaching this distributed systems class, I'm obsessed with using monotonicity to reason about program outcomes despite non-determinism in their executions. That's kind of my thing. And monotonicity, sort of in simplest terms, means monotonic growth of knowledge. As I get more inputs, I just produce more outputs. I never have to retract outputs. I never revise my conclusions, right? And there's a kind of interesting, maybe tantalizing, maybe it's a dead end, connection between knowledge-based protocols and monotonicity, right? Because as I presented this hierarchy, I kind of naively presented it like we're doing the itsy-bitsy spider up it. We don't go down, you just go up, right? But of course, it's not that way in real life, right? And let me illustrate what I mean. So like, Henry in his talk talked about commit protocols and consensus protocols. They smell similar, but they're different, right? In a two-phase commit protocol, we start out with a lot of uncertainty. And we accumulate knowledge monotonically. People send messages, And eventually, there is a point in the execution at which the coordinator has knowledge of what the outcome of the transaction should be. And at that point, he can tell everybody to commit the transaction. Something else happens at that exact point when the coordinator has knowledge. The algorithm becomes not fault tolerant. The very moment at which the coordinator knows what to do, he becomes the single point of failure in what was, until that point, somewhat robust to failure protocol. So protocol goes from, as we accumulate knowledge, there's a point of no return when the protocol becomes not fault tolerant. That coordinator crashes, everybody's left holding locks, not knowing the outcome of the transaction. Total chaos. Consensus, on the other hand, doesn't have that property, right? Consensus doesn't have a single point of failure. It's fault tolerant. But consensus doesn't necessarily terminate, because in consensus, receiving messages doesn't only add to your knowledge, it sometimes takes away from your knowledge. The case in point in FLP is like, you're a fault-tolerant system that has to distinguish between delay and failure, even though you can't. So at some point in an algorithm, you haven't heard from somebody for so long that you decide he's dead and you get on with your life without him. You do something different. And just when you decide that, you get a message from him. So you go back to an earlier state of knowledge and you go up and down, right? So I feel like there might be something fundamental about monotonic growth of knowledge being at odds with fault tolerance. I don't know. What do you guys think? If you're interested in monotonicity and using monotonicity to analyze systems, there's a great paper about that, CITER 11, Consistency Analysis in Bloom. Okay, so in closing, there's some things I want you to remember. Knowledge is a dual of possibility. I don't have anything else to say about that. I just wanted to say it again because I think it sounds cool. Knowledge gives us this unique lens to analyze sort of protocols in themselves, right? Because all a protocol is, like a protocol that humans carry out, is a recipe for how you take action based on knowledge. Even more tantalizing, knowledge gives us an angle on the matching problem of protocols to properties, because knowledge can characterize the properties, the place that we want to get to in that ladder, and then start to think about what protocols actually get you there. That's really cool. This is more for the academics in the audience, but I think a pretty slam dunk way to start down the road toward a Turing Award or a Dijkstra Prize or a Goodall Prize or whatever is to pick a logic that captures a domain you're interested in, look really hard at its mathematical semantics, and then find a rich correspondence between that semantics and something in the real world, structures in the real world, tables and databases, state machines, representations of distributed executions, and then, profit. And then finally, kind of the main point of the talk and the main point of Halpern's work is like, common knowledge is a thing. Sometimes you need it, often you don't. You can't get it, but you can start with it. And you can find weaker versions of knowledge that get you exactly where you want to be. That's all. Thanks.
So we're going to give people like maybe 2 minutes for a bio break if you need it, and then we're going to do questions. So, the bathrooms are around the corner. Yes. So 2-3 minutes. Come back. Also, there's beer in the back if you want to come back with your beer.
There's beer where?
All right, people. I wasn't joking when it was like 2-3 minutes. Who has questions for Peter? Okay, Lindsay.
It's this, right? So instead of saying I have a set of worlds, I said that I have a set of runs. And so it doesn't actually, it's a little bit of an abusive notation. It doesn't exactly type check, right? Because R is sort of a set of sets of worlds. Because some proposition is true or false in a run at a time. So over here in the sort of canonical crypt key structure, W is a set of worlds. Yeah, well, I is a knowledge interpretation. And IRT is a point in a particular run in a particular time. So I is going to contain all of R, right? So all of the RTs are in R, right? So I is sort of just our knowledge interpretation. And we talk about projecting a knowledge interpretation down to a particular point in a particular run. But that's exactly where we're interested in, is P true, is Q true, and so on. Okay, let me see. I mean, try to connect the idea of what the world was in the crypt key structure to what it is here. Right? Because this is like an extension of a crypt key structure based on our model of a distributed system.
Like in your setting, what are worlds? Are they like the memory that are in all the different processes, or?
A world is a global view of the propositions that are true in a run at a time, right? So a processor deciding if they know something is starting in a particular run at a particular time and considering all the runs and times that they think might be possible and seeing if they agree about the truth value, because once we have a run and a time and a world, we can ask if a particular proposition is true. We're asking what propositions have the same truth values in all worlds that are indistinguishable. Yeah, I mean, so sort of intuitively, the way I was thinking about it is that, yeah, so, like W is a set, and R is sort of a set of sets. Is that?
Well, sure. Yeah, but like, I don't know, like I'm used to thinking of like a world would be something like, this is the state that memory is in, and you can get from this state of memory to this other state of memory according to its accessibility relationship.
Yeah, right, so that would be like an interpretation of temporal logic in a single site, right? Yeah, no, I think that's a fair point. I think that I rang a lot of bells about how the trick is all about correspondence to something intuitive and a real structure, and this one feels a little bit arguably less real than a database or a state machine representation of a single of a single site program. Yeah, totally, that's true.
Can you tell us again about the significance of the paper, what your feels were about it?
Like what I was saying to you just now. Yeah, well, so, I'm an nth year graduate student who's written a lot of papers, but most of them are like pretty blue sky. And so I'm at a point in my life where I'm like, well, what is impact anyway? So people aren't running my shit, Are they being inspired by my shit? And so like papers like this are really, close to my heart, because here's a paper that's like the most genius thing ever. They won lots of accolades for it. They won the Goodall Prize for this work. But impact and adoption? I don't know. There was a flurry of activity after the paper was published, and this guy Interlandi is doing cool work, and it's a neat thing to think about. When you read the paper, you're never the same again in terms of how at least I was never the same again, thinking about how systems work and how to reason about them, but it's not clear how to measure the impact of this work or any blue sky work. I'm curious what you guys think about that. Like, especially in a community where, at least ostensibly, we're gathering to discuss reading papers as a art for art's sake kind of thing, like reading papers just for the hell of it. Is it okay for papers to stimulate the imagination and not do anything else, even when their subject is programming? Like it should be, right? It should be changing the way we program, and if it doesn't, how do we measure it?
But hasn't this happened before? Like, I mean, haven't we been in parts of computer science that just like pushed it, like kind of like took a seat, and then somebody else like picks it up like 40 years after. It's like, that idea over here. Just like maybe we just need the person that comes after us for like collective intelligence, maybe creates a next like hybrid humanoid or something, and they're like, that thing that we saw. Hasn't this happened? I mean,
Yeah, I believe that. I think like if we take the long view and we're not selfishly concerned with our own, marketability and reputation and all that kind of stuff, because we only live for so long, we might not take that much comfort from that. But I think if we care about the zeitgeist progressing towards knowing itself, then that's great. I mean, we are it is science, right? Or at least it's partly science, and so we are moving forward monotonically through the space of knowing things collectively. But that doesn't necessarily give somebody any comfort who's written a lot of great papers, but nobody actually cares.
so you want the tombstone thing?
Yeah, exactly. Or maybe even before that, a little bit of recognition.
The money. Anybody have any questions?
How would you relate the point you made about belief to the fact that some of this knowledge might be erroneous? When you talk about
Can you hear him?
knowing about knowing, and it's not only growth of knowledge as well, but in this system, it's often the case that there's no single truth, and the state of one machine, for example, or its accessibility might be true for one and not for another. And in many cases, like I learned that the problems we are in systems are often linked to erroneous beliefs and actions that are based upon such beliefs. So partitions are one example of that. In some cases, you might end up in a situation that's indistinguishable from business failure, where someone knows something that's completely wrong and will act on that and go on.
Yeah, so I mean, I kind of have two reactions to that. I honestly haven't thought very much about studying indeterminacy using a belief-based epistemic logic rather than a knowledge-based one, but it's certainly an interesting thing to think about. That's the first answer. But I don't have anything smart to say about it because I haven't given it any thought. The other sort of answer is, I suspect that Halpern and Moses might have sort of dismissed the problem as an issue of like what you happen to have axiomatized before you go to study the system, right? So like a split brain scenario that happens among replicas due to a partition could be cast, as you did logically, as an issue about incorrect belief. Or in a pure knowledge-based interpretation in which we rule out belief axiomatically, it could just be cast as a broken protocol that didn't achieve the requisite level of knowledge to safely do an update. So I think there's kind of two ways of looking at that. We embrace the uncertainty and use these frameworks to study indeterminacy, belief, as a thing that processors have. I think for Halpern and Moses, they just ruled it out. They said processors don't have belief. There's uncertainty and then there's knowledge. And if you do something before you have knowledge, yeah, you might get an incorrect execution. Right, assuming that we've accepted the axiom, which they ask us to accept when we start reading. But I mean, this isn't obviously true. This is philosophy. I mean, we could debate this all night, right? Is it true that you only know true things? It depends what you mean by know. But so, because knowledge and belief, because epistemic logic has the same semantics, we could study belief instead of knowledge, and that could be really rich. Yeah. But Halpern didn't do that. And I think their answer to that would have been, no, we only call things knowledge when they're the true things. And the states of belief that we progress through on the way to knowledge, we don't take action based on. And that's how we get correct protocols. An interesting angle actually would be a hybrid language where have speculative protocols, right? Protocols that like believe something and they have some resources to spare, so they do some computation, but they don't take side effects because they know that it might be falsified. Then when they attain knowledge, they either dispatch the speculative computation or clean it up. Transactional memory. You can imagine lots of interesting hybrids actually enriching a language like this with operators for both belief and knowledge.
So if you look at this as an example, you're passing knowledge across the audience, right? And so how do you know that we know everything you've told us unless we ask questions? So two people that ask questions, I feel like it's a very lossy system that we have here.
That's right. I mean, if
Those people who actually read the paper, right?
yeah, so absolutely, that's great. And that's like the kind of thing that a philosopher would say in a philosophy class. I think that like when we look at it from a protocol design angle, usually protocols dictate with strict constraints about the messages that can be sent. And so if we were trying to devise a protocol in which I could know for certain if you knew what I know this thing. I do this talk, I want you to know it. How do I know if you know it? Well, I need messages, right? Because that's the only way I increase my knowledge. And I would want to enforce that we used a protocol, that the messages you sent to me were rich enough that I could know for certain. Or I would ask you questions, or whatever it might be. But yeah, you know, if it's completely random, the exchanges that we have, it would be a stretch to call it a protocol. Although in real life, we usually don't follow strict protocols. And yet, we move forward in the knowledge hierarchy. I mean, does that at least address, if not answer?
I don't know if I was asking a question or just kind of throwing something out there.
That was a good thing to throw.
Any more? Yes.
So when you talk about a cut in your system, you always draw a horizontal line across your vertical lines. Doesn't that sort of implicitly assume that there is some kind of notion of simultaneity across your nodes?
Yeah, I knew somebody was going to say that. Yeah, I don't know. This is the formalism that Halpern uses. I think that it's not fundamental. You don't have to draw that line horizontally. You can draw that line any old way. Just pick a point on all the lines, and we can still talk about the knowledge state. Yeah, or in a diagonal or whatever it might be. I don't think it changes anything, but I'm not 100% confident about that. It's a good question.
When you were talking about the assumptions that you had to make your proof hold up, one of those assumptions was simultaneous agreement. Yeah, what does that mean?
Well, in the context of two generals, it's easy to answer that, right? The generals, as I said in the setup, are sure to fail if they don't attack simultaneously. So the type of agreement that we needed to come up with a solution, to come up with a protocol that solves two generals, was an extremely strict form of agreement, that common knowledge needs to not just be achieved, but needs to be achieved essentially simultaneously at both parties, right? And kind of that made it really easy to prove that it was impossible in real life. So in the paper elsewhere, we didn't have time to get into it, but they define weaker forms of common knowledge, like eventual common knowledge. Like there's a thing that is common knowledge, but people are going to asynchronously learn of it. And it turns out that you can't use that to solve two generals either. Probabilistic common knowledge, right? Where you assign likelihoods of common knowledge being attained after a certain number of rounds or whatever. But I mean, I guess that bullet point was there to just to argue that, you know, we throw agreement around, but agreement means many, many different things and represents many different points on the water spout that the spider goes up or whatever.
I just have a basic question. What does he mean when he says SBA? I didn't see the...
What does he mean when he says?
Well, he says, like, for example, a knowledge-based protocol may often be a very useful, high-level way of describing the right actions to take in the case of SBA for other problems.
SPA?
SBA.
Oh, simultaneous Byzantine agreement.
Oh, okay.
So simultaneous agreement, plus you think everybody else who you're communicating with is trying to fuck you, right? So lying, saying, you know.